Hi, I'm Debbie Nelson with Nixene Publishing here in the United States. And in continuing our series on graphene, we're going to divert just slightly because we have Adrian Nixon, who is editor-in-chief of the Nixene Journal. And we also have Dennis Wright, who is a board member for ISEC, which is the International Space Elevator Consortium. So welcome, gentlemen. We have Adrian coming from Yorkshire, England, and Dennis coming from New Mexico.
Hello, Debbie.
Thanks, Debbie.
It's great to see both of you. Thank you so much for taking your time to record with us today. Dennis, tell us a little bit about yourself, because everybody knows Adrian.
I am currently the vice president of the International Space Elevator Consortium, and I've been a member of that group since 2013. And I am working on things like simulation of the space elevator. My background is in nuclear and high energy physics. So that's what I spent most of my career doing, experiments at Stanford, at the Large Hadron Collider, also doing simulations. It seems that I continue to do simulations, but I've just changed my focus from quantum mechanics and high energy physics to very interesting astronomical scale structures.
That's quite a giant leap.
Yes, fortunately, physics applies to the micro and the macro, so it's good for me.
Well, thank you. It's great to have you here. Adrian, you have a few more skills and a few more hats that you wear too.
Yeah, most people will know that I'm an industrial chemist by background, and also involved with the Nixene Journal, where I'm the editor, but also I'm a board member of the International Space Elevator Consortium as well. So I work with Dennis. My area of speciality is looking at materials that could be used to make the tether.
All right, well, let's hear a little bit about what the space elevator is.
Yes, it's a way to get into space without rockets and to use the rotational energy of the Earth to boost some payload into various positions along the elevator. And so essentially you have a long tether or ribbon. It, of course, is subject to the gravitational force, but luckily the gravitational force goes off by 1/r², so it falls off rather rapidly. That's still not enough to help you, because you need something else to pull that string out. And so for that, we have the centrifugal force. And you can sort of imagine, if you ever played the old trick of tying a string to a bucket and then rotating the bucket horizontal to the surface of the Earth, and notice that the water in the bucket doesn't fall on you because the centrifugal force is holding it in. And so the same kind of thing works for the space elevator. You can get that outward tension to counteract the gravitational force. The key thing there is we need something to make the ribbon out of, which is very, very strong. And that's where the graphene comes in.
So Adrian, that has to be the cue to move on to you.
Yeah, that's a really good introduction, Dennis. Thank you for that. So we have a satellite orbiting the Earth, geostationary, so it's above the same part of the Earth all the time. And then a tether or a piece of material comes down and connects the satellite with the surface of the Earth. And actually, it goes beyond the satellite out a little bit further. And as Dennis says, it's a bit like swinging a bucket round on a piece of string. NASA looked into, is this science fiction or is this a reality, about the turn of the century, I think, wasn't it, Dennis, with Bradley Edwards doing feasibility studies for NASA.
That's right. That was a NASA Advanced Concept Study.
That's right, yes. And NASA funded it quite significantly, so it was a fairly robust piece of work. And basically they found that all the elements of the space elevator are doable with today's technology. So you can build a bit on the ground, you can build the bits in space. There's already 500,000 kilograms of material up and orbiting with the International Space Station. So we can get stuff up there fairly easily, and we can build things in space. The sticking point really was the material you make the tether out of. And at the time, there was only one candidate material that was strong enough in theory, and that was carbon nanotubes. Everybody piled into that and had a look at it, and they sort of began to lose a little bit of heart, because this one remaining piece of the puzzle, the materials science for manufacturing these carbon nanotubes long enough and strong enough, hasn't really materialized, has it, Dennis?
It hasn't, and that was, as you say, kind of disheartening, because we thought that given the, if you plot the length versus time, the length of carbon nanotubes was growing rather rapidly from the microscopic to the macroscopic, and then it sort of stalled out for various reasons due to the manufacturing process. And so we were looking for something that could achieve macroscopic size and still could have production by industrial methods, because we're going to need a lot of it.
When we say a lot, Debbie, we're talking about 100,000 kilometers.
But it's extremely light, right? So that when you're moving this material, it's not as heavy to.
Well, it's the lightness is important for several reasons. Yes, you want to get it up there in some reasonable number of launches, or however you want to get it into orbit. But it's also important in the dynamics of the space elevator, because you have to have something not only which is strong, but something which is very light. So if you were to build the space elevator out of steel cable, then basically there is no amount of steel available which could actually support itself. It would collapse. So you need both strength and lightness.
How are we going to make, something like that? I mean, is this something that's doable? What's coming next?
Okay. So carbon nanotubes, the industrial production of them seems to have stalled. So they've reached some kind of limit at the moment, and the work is, there doesn't seem to be much progress being made. About the longest they can make an individual nanotube is about 500 mil, which is probably about that long. And we're going to need much, much more. Since NASA did this feasibility study, graphene was isolated. So the study was done about the turn of the century. So was it between sort of 2000, 2003? Was it about that, Dennis?
That's about right, yes.
Yeah, so a year after the feasibility study was published, Andrei Geim and Kostya Novoselov isolated graphene. And in 2004, Nobel Prize was won in 2010. And as a result of that, loads of interest has piled into graphene. And at the moment, it's made as powders, so they're not really very useful to us. But people have been experimenting with industrial production techniques. As you and I know, Debbie, and Dennis too, the capability to produce graphene at scale now has been progressing at an astonishing pace. So we're now seeing that graphene could be made as a perfect single crystal. And this is a single crystal here just means a perfect sheet of graphene. The Chinese have proved that this can be made at a length of at least 500 millimeters long at the minute, by 50 centimeters wide. And then this year, the Koreans came out of a dark project and publicly announced that they've been able to make graphene on copper at speeds of about 1 meter a minute and lengths in terms of kilometers. So we know that graphene can be made by industrial processes and fast. Problem is, at the minute, it's stuck on copper foil. So it's stuck on the metal, it's got to be got off. But we know in principle that graphene can be made long enough and fast enough. And this whole field is moving really, really fast. So people are starting to get very excited.
Yeah, that is exciting. Now, I remember that a few years ago, Elon Musk looked at the space elevator concept.
Yeah, I think he said he'll wait until he's got a piece as long as a footbridge, which I assume is about 3 meters, and then we'll talk, which is actually quite a sensible thing to say. So at the minute that we can make pieces of graphene much, much longer than that. But the problem is we've got to get them off the metal foil in one piece to be able to present to him and then say, here we are. But given that we're making astonishing progress just in the last few years, we're seeing the industrial activity is ramping up. So, well, as you and I know, Debbie, we're just having to run fast to keep up with the rate of production of this stuff at the minute.
Well, Dennis, do you have anything that you'd like to, expand on as far as any of this goes with the graphene and
I guess I would just go back to, I think, the first talk that I ever heard Adrian give at the Space Elevator Conference in Seattle. And it was kind of an eye-opener for me. And he talked about all the properties that graphene has. And I had no idea. I had heard of graphene just briefly. I didn't know much about it. But not only is it light and strong, but it looks like it has amazing conductivity and capacity to carry large currents. all of these things could be essential for the space elevator. So we're looking into various means of how to power a climber or an elevator car that would somehow grab on to this ribbon of graphene. And if we can manage to transport current through it, that solves one very big problem. Also, we could think of the fact that, you know, it is highly conductive. You could also take advantage of the fact that this is in the environment of a magnetic field, which is changing with time, and that induces currents. And so I think there are all sorts of other opportunities besides just the strength, which is obviously the first thing. But if we can take advantage of the electrical properties of graphene as well, that'll be a big plus for us.
Yeah, that's great. And when you're talking about having a tether there, I know that there's been some mention of space debris and concerns about things like that. But it's my understanding that there are other entities that are going to be handling space debris so that you can focus on doing what you're doing, which looking to construct this and have it be operational.
Space Elevator Consortium did a study on the space debris problem, and it sounds like it's very much a manageable problem. But even more so perhaps that it looks like graphene tethers have a relatively high resistance to impact. So these things may withstand small objects at high velocities. Of course, that's the main problem with space debris. It could actually take these impacts and not be destroyed. So that's certainly not going to be the case for very big objects or something really fast. But if we can reduce the effects of the impacts, even though we know we're going to have some, then that's a big plus as well.
Yeah, exactly. Well, this is exciting stuff because it sounds like science fiction, but it's coming toward reality at as Adrian says, at an astonishing pace. Mm-hmm. And I don't think that people realize sometimes how quickly the technology is advancing.
We have that exponential curve we're looking at. Yes, things are going fast. Yeah.
All right, Adrian, last words?
Yeah, as Dennis said, graphene has lots of properties. You and I, Debbie, know it's basically a Swiss Army knife of materials when you come to look at all the different things it can do. So it's, as well as being electrically conductive, it's very robust. Space junk will probably bounce off it, the smaller stuff. And we're actively looking at other things that graphene can do, which may give us extra leverage in situ as well. So it's exciting, it's developing fast. It's interesting that I'm now associated with a bunch of really, really bright guys around the world who are actively working on this. I find it thoroughly exciting.
Yeah, I do too, absolutely. Thanks so much, everybody.
Thank you.
Thank you.